Okay, first we have Gungun. Gungun, tell me one thing about something about the Rutherford's atomic model. Anyone else? Yadeep?
In Rutherford model, a thin gold foil was bombarded with some alpha particles. In the alpha particle scattering experiment, most of the alpha particles passed directly through the gold foil without any deflection. However, some were deflected through small angles, and 1 out of 20,000 alpha particles deviated nearly equal to 180 degree.
And what were the observations behind this? Who would describe what were the observations behind this? What we have studied in the Rutherford's model?
The observations led to the discovery that the atom has many spaces around it, and the electrons revolve in the orbits.
Very good. Anything else?
And he compared the orbit with the solar system model.
Yeah, exactly. Okay, very good. Bachi, what's your name?
I'm Yadeep.
Okay, Yadeep, very good. So basically, in Rutherford's atomic model, as Yadeep has explained, we have 2 to 3 observations. That first of all, our atom is not completely packed up with the mass, as Thomson's model explained. It's basically most of the space is hollow over there. It has more than space. Just a little bit nucleus is concentrated over a small space. Okay, first thing was this. Second, he has described that electrons are moving in the orbit around it. Okay, very good. That's very quite fine. Third thing which he did not explain was that due to some positive charge, our deflections were due to some angles. That means there is the nucleus present over there, due to which there is some positive charge over there, due to which our space is getting deflected. We can say the radiations are getting deflected at some angles. Okay, so this was all about Rutherford's atomic model explained in our this class. We are going to discuss our new topic, that is Bohr's atomic model. Okay, so let's start with Bohr's atomic model. Bohr's atomic model has explained many things, and yet some things were explained as previously in the Rutherford's atomic model, but he has explained this with little bit modified type. Okay, so he has explained the same things but with little bit modified type. Okay, so what he has actually observed, first thing he said that yes, there is a nucleus present over there and the electrons are moving into the orbits which we have named the circular paths. Okay, but he has told that these orbits are fixed. These orbits are fixed with, that means these are stationary. These orbits are not moving. See, students, in Rutherford's atomic model, the biggest limitation was that we have observed that if these orbitals are moving, after some time their energy would be decreased. Okay, and if their energy would be decreased, our electron would be just jump into the nucleus due to the force, or due to the attractive force of the positive charge towards the electron. Okay, so this was explained by Rutherford. So Bohr explained it in little bit modified type, saying that these orbits are fixed. That means these are stationary, these are not moving. And he also explained that these orbits have somewhat thickness, these orbitals have somewhat radius. Okay, that's why I have tried to show this in little bit, darker type. Okay, so first point, he told us that electrons are moving around the nucleus. Electrons are moving around the nucleus in fixed or stationary orbit. Okay. Second, he told us, as I have already told you in the last lecture, he told us that these orbits have somewhat energy, and this energy can be changed if we radiate them with somewhat more energy. So I would say if I'm just radiating our electrons, our orbits with somewhat energy, these orbits can, the electrons can jump from this state to the higher state. So he explained the same concept which we have described in the previous class. Okay, he explained that we have explained in the line spectra. So explained the same concept that the electrons can jump after radiating, after getting some energy from one fixed stationary orbit to another fixed stationary orbit. That was the second point. And he also said if he radiates the energy back, if he loses the energy back, the electron would come back to its original stationary orbit. Okay, so can jump from one orbit to another by just getting the energy. Orbit to other by getting somewhat energy, and it would be okay. This is the second point. Third, he said, as I have already described you somewhat, that these orbitals have, no, sorry, not orbitals, these orbits have somewhat fixed thickness. So that means there is a kind of radius involved in this orbit. And this radius is observed to be 0.529 angstrom, which is also known as Bohr's orbit radius. And I would say this would be the first Bohr's orbit radius, because as we will keep moving, the energy, the electron would be keep moving, because these have been numbered. In the third postulate, we will study that the energy that these have somewhat fixed radius known as the Bohr's orbit orbital. Besides this, he told us that as we know very well, delta E equals to h nu. That means we have different energies of every orbit, and we can say simply that mu equals to delta E over h. If I'm not writing something wrong, no, it's true. Mu is equal to delta E over h, or we can say E2 over h minus E1 upon h. What E1 and E2 explains to us? E1 and E2 explains the energy of first fixed orbit and second fixed orbit. Okay, these were the three postulates. Besides this, he also told us that these electrons are moving into a circular orbit. That means they must possess somewhat angular momentum. I will repeat it again, that since these electrons are moving into a circular orbit, that means they must have somewhat fixed angular momentum. And this angular momentum is denoted by mvr. I hope you have heard about angular momentum in physics. Momentum is just P equals to mv, and angular momentum is denoted as mvr. And this mvr is integral multiple of somewhat, we can say, constant, which is multiple of n h upon 2 pi. This one is the, okay, this one is third postulate, this one is the fourth postulate. Angular momentum, that we have mvr, and this is a fixed constant, this is multiple of fixed constant known as nh upon 2 pi. These all postulates were given by the Bohr, in which we have observed that yes, there is nucleus, quite true, electrons are moving around it, quite true, but the electrons are moving into the fixed orbit. The orbits are not moving, they have somewhat fixed kind of energy. Okay, and these electrons can easily jump from one orbit to another orbit by getting some energy. And if they lose that energy, because they cannot be longer for some excited state for the longer time, so they would easily come back to their original position. Okay, third point, he said that as we know delta equals to h nu, so we can differentiate these two orbits on the basis of energy. Okay, and finally he told, as the electrons are moving into the circular orbit, that means they must possess some angular momentum known as mvr, which is integral multiple of a fixed numerical quantity n, where h is known as your Planck's constant, and n, what is n, we will see in our next postulate. Okay, these were the basic postulates. Beside this, he has put some, sub basics, we can say, or subsidiary postulates. Okay, these were the main postulates. I hope I'm clear with this topic. Now let's move to these 2-3 postulates more, in which n is explained very well. Okay, so what n actually wants to explain us, he wanted to say that this n is named as, for each orbit, this n is integral and integer, and it could be 1, 2, 3, and so on. That means this n equals to 1 represents first orbit, this n equals to 2 represents second orbit, and this n equals to 3 represent third orbit. Okay, so in this case, you can now easily distinguish, you can easily get why did I say that this angular momentum is integral multiple of n and h upon 2 pi. Okay, now in the very same order as he have explained, these orbits have some kind of radius, so the radius concept was given as r equals to n square a naught. If I'm talking about the first one, I have already told you, okay, this a naught equals to 0.529 angstrom, which is known as Bohr's orbit radius, or first Bohr's orbit radius. Why I have told the Bohr's first orbit radius? Okay. Why I have told the Bohr's first orbit radius? I hope now you have got that. This is because the reason behind this is, if I put n equals to 1, the radius would be equals to 0.529 angstrom. Okay, same as it is, as I will keep moving, n equals to 2, n equals to 3, what would be the 4 into a naught, that is 4 into 0.529, same as it is 9 into 0.529, same as it is 16 into 0.529, and so on. That means we can say that our electrons are getting away from our nucleus. As the number of n capital increasing, our electrons orbit are getting away from the nucleus. Okay, this was also explained very well by Bohr's atomic number. Okay, fine. Also, in the last class, we have observed in line spectra some n1 equals to 1, n2, n1 equals to 2. That means the Lyman series, the Balmer series, the Paschen series. This was also explained by Bohr. Let's see how. Okay, as I have already told you that these energies can be differentiated by energy from n1 equals to 1 to n1 equals to 2. So in the same order, he has explained En equals to minus RH1 upon n square, and represent final and initial. That means if n1 equals to 1, this is my initial orbit in which electron is right now present over. If he would be radiated, if he would get some kind of energy, he would jump to the final state, that is n equals to 2. So we have EF, which represent final energy. We have EI, which represent the initial energy. So in short, we have 1 over nf square and 1 over n initial square. Okay, now if we have to differentiate these two terms, we have to differentiate the energy. What we get? We will get delta E equals to minus RH 1 over n initial square minus 1 over nf square. Okay, I have written something wrong or not? No, it's true. because minus sign would be cancel out here. Okay, so just we have done that. If we differentiate our energy, if we put some difference of the energies, we can easily calculate by this formula. This RH is known as Rydberg constant. In the last class, we have put it as 109677 centimeter. If we put in joule, we will get some numerical quantity. Just check out in the book. That's not so much important. But the point this, we have some numericals which we have discussed, like we are having Lyman series, Balmer series, Paschen series, just on the basis of this initial and final. We will be given that what is Ni and what is Nf, and the RH Rydberg constant would be also given. So you can easily calculate. Okay. Besides this, if we have to calculate the frequency, we know very well delta E equals to H nu. This formula we have been going through so many times. So we can easily calculate H nu equals to RH 1 over N initial square minus 1 over N final square. With the help of this, we can calculate R nu because H is also our Planck's constant. Okay. So I just want to explain you that Bohr's atomic model have satisfactorily explained the concept of orbit as well as energy, as well as difference in energy and the frequency. Okay. Besides this, he have also told us that these orbits have somewhat thickness. That means they must have some radius. Okay. So these all postulates and sub postulates were very successfully covered by Bohr's atomic model. I hope I have made sense with this topic. And if you have any kind of doubt, please let me know after some 5 to 10 minutes. Besides this, let's see, is there some more left also? Yes. The one thing which I haven't explained yet, which is also explained by Bohr's atomic model, is here we have taken the concept of hydrogen atomic model. We have just taken E equals to minus RH 1 over N square. Now, what would happen? Let me do this. He had given us energy equals to minus RH 1 over N square. Okay. Now, what would happen if we go to the some complex atoms, to the some complex molecules, like we are just talking about hydrogen? What's happening if we are taking lithium, beryllium, boron, calcium, magnesium? Can these also be explained by Bohr's atomic model, the energies? Yes, this is also explained, not so satisfactorily, but he explained by putting another number which is known as E equals to minus RH Z square over N square. So this is for hydrogen, and for higher atoms, he said E equals to minus RH Z square over N square. What Z wants to explain here? Z equals to atomic number. So if we put for the lithium, Z would be 2, for the beryllium, Z would be 3, for boron, it would be 4, and so on. Okay? So Bohr's atomic model has successfully explained these all concepts. Should I revise, or you have got all the points? Stationary orbit can jump from one orbit to another, so we can differentiate the energy. These have fixed orbit, so these have somewhat radius also, and they have angular momentum too. Okay, these all were explained by Bohr's atomic model. Now, as it have explained so much points very carefully, very satisfactorily, since it had some drawbacks too. See, class, as you have observed in this particular chapter, chapter number 2, structure of atom, if I just leave the topic discovery of electron, proton, and neutron, as these were the theoretical topic, okay, if I just leave them. Now, if I'm going to another topic, the second topic in this chapter was atomic model. And you have observed that these all atomic models are just interconnected with each other. What we have done, Thomson's atomic model. We have observed them. We said it has limitation. We just avoid them. Then we move to Rutherford's atomic model. He explained us, he gave us some points. We put those points, but he had also drawbacks. We left them. Okay. But meanwhile, with models, we came to know so many important topics like atomic number, like mass number, isotopes, isobars. Okay. Same as it is, as the Rutherford's atomic model was rejected, we have to came to know about the dual nature of matter and light. We have observed that light cannot have only the wave nature, it must have the particle nature too. This was explained only if the Rutherford's atomic model was rejected. It has some drawbacks. है ना? अगर इसमें कुछ drawbacks ना होते, we didn't came to know about the particle nature, about the dual nature. So all these models have some things that I want to explain. Now, same as it is, we have Bohr's atomic model have explained us so many points, but it has also some drawbacks. So we have to reject it. And what are its limitations and what these limitations lead to? This is our new topic. Okay. So please have a focus on this chapter. This is very important and easy chapter, and try to concentrate that what we are going to study over here. We are just putting up a model. We are grasping some important things over there, and then we are rejecting due to some limitation. Same as it is, we're moving to next model, to the next, and so on. But meanwhile, we have so many important concepts, so many important topics, only due to limitations of these atomic models. Okay, this is all I want to deliver. All right. Now, what could be the drawbacks or the limitations of Bohr's atomic model? See, this have explained us quite obviously very important things, very important all the postulates, but it has some limitations known as Zeeman effect and the Stark effect. These were two scientists, the Zeeman and the Stark. These told us that yes, Bohr has explained us quite well all the things, but he did not explain what would happen if we put some electrical charge or some magnetic field over our atom. That would our electron would be deflected, or would they show somewhat different behavior if we put them into our electric or magnetic field. Okay, a few days ago, I think yesterday, a student was asking the same question, and I appreciate that students are studying chemistry and they have some doubts and queries. That's very good thing. So these electric field and magnetic field, due to which our electron has some deflection, has some points, that is our new topic. So these were the limitations, that the electric and the magnetic field were not explained. The effect of electric and magnetic field over the electron was not explained by Bohr's atomic model. Okay, so we need a more better concept, a more better model, which is known as quantum model. Okay, as I already told you, somewhat concept, somewhat idea about quantum. What are the quantas? What are the packets of light? So we will lead to new topic, that is the quantum model. But before going to that particular topic, I have two different topics. First one is the Hinsberg uncertainty principle, and second one is known as our de Broglie equation. So first we will just discuss de Broglie equation. That is just a simple equation, and we will see 1 to 2 numericals over it, and then we will finish our class after having your doubt, quite obviously. Okay, just see a simple equation known as the de Broglie equation. De Broglie equation. There was a scientist known as de Broglie. He just told us that there is a relation between lambda, that is wavelength, and the momentum. He told us that there is a relation between the lambda wavelength and the momentum, and we know momentum, that is small p, is equals to mv, mass into velocity. So lambda equals to h over mv. This was all about the Broglie equation. With the help of this equation, we can easily calculate our velocity, we can calculate our wavelength, we can calculate our mass, or even our momentum. Okay, so this was known as de Broglie equation. Let me see a numerical, a very simple numerical over it. The first question in your textbook is, what would be the wavelength of a ball with mass 0.1 kg moving with a velocity of 10 meter per second? So lambda equals to h upon mv. You know very well what is h over here. The Planck's constant, 6.6 into 10 raised to power minus 34. The mass is given as 0.1 kg, and the velocity is also given as 10 meter per second. We can easily calculate lambda. So simple. But what we have done, we have second in which, and the kinetic energy is given, and we have to calculate the wavelength. So the mass is given and the kinetic energy is given. So can we calculate with the help of our kinetic energy the velocity? Yes, we can calculate. We know very well that kinetic energy equals to half mv square. The kinetic energy is given, suppose it is given as 3 into 10 raised to power minus 25. This is another formula. Mass is given 9.1. We can easily calculate V from here, and then we would put in this equation what we get, the lambda, the wavelength. So this was all about the de Broglie equation, which is just a simple numerical formula. And on this formula, we have some numerical formulas in your which are very important for your exam point of view, as well as your competitive exams too. And this was all about Bohr's atomic model and de Broglie wave equation. So this was all about the class. Now tell me something if you have any kind of doubt or queries. Or should I explain a little bit more about this topic?